or mating systems. And you have seen your WhatsApp there. I have sent a write-up also, some reading materials, right? So you just download those things. Here, what is selection and what is breeding system here? What we want to do in the animal breeding program is, animal breeding here means which animal should be bred with which animal. It means a planned genetic alterations of the population so that the animal can better fulfill the demand detected by the production requirement. Means here is we have to plan certain ways which of the animals will be bred with which animals to meet out the requirement of the human populations. So here, this genetic improvement in farm animal involves, first is selection, as we have discussed already. Here is choosing the best animals to act as the parents. Then once they are selected, these males and the females which have been selected, in which way which male should be bred with which selected female. That is known as mating system or breeding system. Now here, different mating systems or breeding systems here means which male with which female. So what is in our aim? That is, we may like to increase the homozygosity, or we may like to decrease the homozygosity in the population. So accordingly, the breeding system may be either to increase or decrease the homozygosity in the population, or we want to maintain the homozygosity as such. Now, various mating schemes of animals classify into two broad categories. One is breeding to increase homozygosity, another is breeding to increase heterozygosity. See here, if there is no selection, that means the population is under random mating. So under a random mating population, as you have learned in Hardy-Weinberg law, that in absence of selection, migration, and the mutation, the population will remain constant in terms of gene and the genotype frequencies from generation to generation. So here, if selection is there, definitely there will be change in the genetic makeup of the population, which may be either increase in homozygosity or decrease in heterozygosity. Now, breeding to increase homozygosity here, inbreeding. First is inbreeding, which we will discuss. Then under the inbreeding, there may be close breeding, strand formation, or line breeding. Then breeding to increase heterozygosity, here it is outbreeding. The opposite of the inbreeding is outbreeding. Under outbreeding, there are different subtypes. First is outcrossing, crossbreeding, grading up, species hybridization. So one by one we'll discuss in then crossbreeding. Crossbreeding means mating between two different breeds. Say Sahiwal is crossed with Haryana. That is known as crossing of the breeds. So here it may be single two-way cross. We'll discuss in detail later on. Three-way cross, four-way cross, or double cross, back cross, sequential cross. Here it may be criss-crossing. Then rotational crossing using 3 breeds or 4 breeds. Then crossbreeding in continuation, it may be top crossing, top crossbreeding, recurrent selection, recurrent reciprocal selection. Here, this recurrent selection and the recurrent reciprocal selection are very important for short type answers. And here, I will not speak here. Then, one is selection with different type of gene action. As we know, there are 2 types of gene action. One is additive gene action, another one is non-additive gene action. So for additive gene action, if the trait is controlled more by additive gene, then the heritability of the trait is high. In that situation, selection is very effective. So for utilization of the traits controlled by additive gene action, we can go for selective improvement, that is one of the best male and the females, and bred them together. Then for non-additive gene, this word dominance, epistasis, gene interaction, you have learned in Mendelian genetics, that comes under this non-additive. If a particular character or trait is controlled by non-additive gene, the heritability is very low. In that situation, selection is not that much effective. So what we should do here, we should breed the animals which are not related. Means distant animals should be bred together so as to exploit hybrid vigor or heterosis, which we'll discuss in detail later on. So now after this, I will talk about inbreeding now. Hello, okay. Anyone please switch on your microphone and tell me slide is visible?
Yes, sir.
Okay, okay. Then inbreeding and its effects, because time is very limited, we have to go a bit fast. Now, as we know, once also we discussed inbreeding is mating between related individuals. So the perfect definition is just in front of your slide, which I will provide. I have already provided in your WhatsApp group. Inbreeding is defined as the mating of animals more closely related than the average relationship within the breed or population. See, for example, in a population, there may be certain relationship. I am more closely related to someone. I am more distantly related with someone. So there is average relationship in the population between two individuals. So when we breed two individuals, if the two individuals are having more closely related as compared to the average relationship in the population, that type of mating is known as inbreeding. So here, for example, parent breeding of parent with offspring, full brother and sister breeding, half brother and sister breeding, all are the examples of inbreeding. Then, if inbreeding is there in a population that is mating between related individuals, then what will happen in its genetic makeup? So, due to the inbreeding, there will be increase in the homozygosity in the population. Homozygosity means similar alleles present in a locus. Then the type of the gene may be either recessive gene, or it may be dominant gene, or it may be harmful gene, it may be any type of gene. We don't have any control. Homozygosity will be for any type of genes. Then there will be decrease in the heterozygosity. As there is increase in the homozygosity, then there will be the corresponding reduction in the heterozygosity in the population. Then what will be the phenotypic effect? Genetic changes is there due to the inbreeding, increase in homozygosity. Then this increase in homozygosity, if it is for those harmful genes, that is harmful recessive genes, then these harmful recessive genes, when they are present in homozygous condition, they will express. So these due to the expression of these harmful recessive genes present in the homozygous conditions, due to the inbreeding in a population, there is reduction in the performance, phenotypic performance of the animals in the inbred populations. So this reduction in the phenotypic performance due to inbreeding is known as inbreeding depression. It may come as a definition or it may come as a short note. This reduction is manifested in many ways, and it depends on the degree of inbreeding. If there is more intense form of inbreeding, then inbreeding depression will be more. Then this inbreeding depression is more for those characters which are having lower heritability. Again, I am repeating, effect of inbreeding depression is more in those traits which are having low heritability. Low heritable traits, more inbreeding depression. Highly heritable traits, low inbreeding depression. Then, What is inbreeding depression? If you say it is happening all around us, here due to the inbreeding, there is reduction in the reproductive efficiency, there is increase in the mortality rate, there is reduction in the growth rate, there is more frequencies of hereditary abnormalities in the inbred population. That's why we want to avoid inbreeding in the population. Then there are negative effects of this inbreeding. Due to the inbreeding, there is increase in the homozygosity irrespective of the type of genes. If the genes are of harmful in nature, then there will be reduction in the performance in the population. That is not desirable from our breeding point of view. That means inbreeding is harmful. Okay, then inbreeding may be harmful for some other characters, but it is still useful for some other characters which are more heritable. So in spite of having this negative effect of inbreeding, that is inbreeding depression, still inbreeding can be used in some of the ways. Let us see what are the possible ways. Now, these points you have to remember, then we have to elaborate it, because inbreeding and its possible uses, it comes as a long question in the exam. First is, it can be used to determine the actual genetic worth of an individual. Here I will tell you, actual genetic worth means whether the individual is having any harmful gene, that is whether the animal is a carrier for a recessive harmful gene. So for that determination, this inbreeding can be used. Then next is, it can be used as an aid to selection, means inbreeding can be used for selection. It can assist in our selection program. Later on I will discuss in detail. Then it may also be used for selection against genes that produce abnormalities or death. Means inbreeding can be used for selection of harmful genes. That harmful genes or deleterious genes we want to remove from the population. In that situation, inbreeding can be used. Then it can be used for formation of inbred lines. Due to the repeated inbreeding in a population, we can form different inbred lines. These inbred lines can be used for exploitation or utilization of the heterosis. Then inbreeding can also be used for development of prepotent animals. Here, prepotent animals means animals which one individual, if he or she is having the capacity to stamp its characteristics to its offspring. So for example, you are more similar to your father. You are more similar to your mother. If you are more similar to your father, that means your father is more prepotent as compared to your mother. If you are more similar to your mother, then your mother is having more prepotent than your father. Then another point is, it can be used to determine the types of gene action. Gene action means additive gene action or non-additive gene action. Then it is used in production of seed stock. This particular seed stock means parent stock is generally used in plants. Now let us discuss in detail this determination of actual genetic worth of an individual. It can be used. See, in animals, you might have heard there are so many abnormal hereditary characters. Say like snorter dwarfism in cattle, hyperostosis in swine, cryptorchidism in sheep. So these many things that is there, these abnormal things which are not desired from the breeding point of view. Due to the inbreeding, these many unwanted characteristics are observed in the population. So in this situation, if an individual is a carrier, if that individual is used as a breeding animal, he or she will transmit this recessive gene present in him or her to the next generation. So in that situation, we want to test whether this animal which is going to be used as a breeder or as a parental stock is having any abnormal or recessive gene in it. So how to identify this one? Then that particular individual that is generally male, because male are commonly used in the animal, then we consider that one male is the half of the population. So that male is crossed or bred with at least 35 of its own daughters. Here you have to remember this minimum of 35 daughters of his own daughters. Then once these 35 daughters are mated with that individual, then we expect around 35 offspring. Out of these 35 offspring, if any of the offspring is having some abnormal characteristics, that reflects, that indicates that that individual male is having a recessive allele which is present in the form of carrier. So in that situation, that male should not be used for further breeding. Then coming to the age and age to selection here, don't go in the slide, just try to listen. When a population is under inbreeding, that population is subdivided into different families. Then inbreeding is keep on going from generation to generation. Then the whole population, which was a single population at the very beginning, now is subdivided into different families. Some of the families are showing improvement in their production performance. Some are showing deterioration in their production performance. Then the individuals belonging to those superior families are used for breeding. That means inbreeding can be used as an aid or assist, can assist the selection program. Then, as I told, if the abnormal genes are present in a population, inbreeding can be used to remove out those genes. Here, if in a population, if some of the abnormal genes are present, abnormal phenotypic characteristics are observed in the population, that means those parents which produce abnormal offspring should be culled from the population so as to remove the abnormal or harmful or deleterious genes present in the population. So this can be identified by doing inbreeding, that is breeding between related individuals, so as to have the recessive homozygote conditions of those abnormal genes. Then inbred lines to exploit heterosis. As I told, in a population, if there is inbreeding, that population is subdivided into different families. Then within these families, there is again inbreeding from generation to generation. Then many inbred lines. One family is now considered as a inbred lines. So in this way, we may develop 5-10 inbred lines from one population. So these inbred lines, once they are developed, some of the inbred lines may be homozygote for recessive alleles, some may be for dominant alleles. We don't have any control. So now these different inbred lines which we develop may be crossed with each other so as to identify which of the two inbred lines are producing superior offspring. Okay, that crossing of the different inbred lines, that is known as di-allele crossing. Di-allele crossing. Your allele, what is there? So that is di-allele crossing. Okay, in that way, we can use inbreeding to form different inbred lines so as to exploit heterosis. Then here, as I talk about the prepotent animal, it may be your mother, it may be your father. This prepotency is due to the presence of dominant homozygote alleles in that individual. As we know, if the individual is having dominant alleles in the homozygote conditions, either of these dominant alleles will be transmitted to the offspring, so expressing its characteristics in the progeny generations. So if the father is having more dominant alleles, then definitely those alleles will suppress the recessive alleles inherited from the mother. So now my physical characteristics will be more similar to the father. That is, my father is more prepotent. Then this prepotency is due to increase in homozygosity for dominant allele. This can be done by using inbreeding. Means inbreeding can use homozygosity. Then determination of type of gene action. Gene action means it may be additive gene action or it may be non-additive gene action. As we know, already I told that if the inbreeding depression is more, that means that character is having low heritability. Low heritability means that character is more controlled by non-additive gene action. Means if the inbreeding depression is more for any of the economic traits, if that trait is more controlled by non-additive gene action. If the inbreeding effect is less or almost nil, that particular character is more controlled by additive gene action. Say, for example, carcass traits, meat quality, dressing percentage, and all those things, they are more controlled by additive gene action. Then your reproductive traits like age at first calving, calving interval, service period, all those things, they are having very low or low heritability, and they are more affected by this inbreeding. That is, they shows more of inbreeding depressions when inbreeding is there in a population. Then coming to the production of seed stock here, mild form of inbreeding, not intense form of inbreeding. That is known as line breeding also. So this type of mild form of inbreeding is practiced in a population so as to maintain a very high degree of relationship between the animals in the herd. Means if mild form of inbreeding is not there in the population, then the relationship among the individuals present in that population will be reduced from generation to generation. But what we want is, as we know, if some of the outstanding individual is identified, that outstanding individual is supposed to possess superior genes. Those superior genes, once they are inherited in the progeny generations, if the progenies are bred with some unrelated individual, that is outbreeding, then the percentage of the genetic inheritance from that outstanding individual will be keep on reducing from generation to generation. So in that situation, to prevent this dilution of the genes from the outstanding animal, we want to go for mild form of inbreeding, that is line breeding, which is commonly used in your dog breeding, cat breeding, like that. So now here I am finishing this. Then hello, now we'll discuss about inbreeding coefficient. Just now we discussed about this inbreeding and its effect at the genetic level as well as phenotypic level, and what are the possible uses. Again, I am briefing about the possible uses of inbreeding because that is very important. First was determination of the actual genetic worth of an individual. Inbreeding can be used as an aid to the selection, can be used for the formation of inbred line, to exploit heterosis, for increasing the prepotency of an individual, for production of the seed stock, and then for selection against the harmful genes present in the population. Hold those points and you try to remember point wise, then try to elaborate in the exam. It may come as a short note and long form. Now, as we know, due to the inbreeding, there is increase in the homozygosity. Homozygosity of different types of alleles, which we don't have any control. The alleles may be dominant, alleles may be over-dominant, alleles may be, if it's this one recessive or any other thing. So this increase in homozygosity due to the inbreeding can be measured by this term inbreeding coefficient. That is the percentage of increase in the homozygosity in a population is expressed as inbreeding coefficient. So then what is this inbreeding coefficient? Dear students, you try to remember this definition, because if the definition of inbreeding coefficient comes in the exam, you have to write word by word this definition. But At the same time, you should also have the idea what is inbreeding coefficient. Inbreeding coefficient is the measure of percentage increase in homozygosity due to inbreeding in the population. So now here, in terms of probability, it is defined as the probability that two alleles at a locus in an individual are identical by descent. That means it is a probability. It is a possibility that two alleles, as you know, in a locus, there are two alleles, one allele from father, another allele from mother. So we want to see in a locus whether these two alleles, one from father and one from mother, are identical by descent. Identical by descent means photocopies. So you can go for xeroxing of a one page. So those Xerox copies are all same, all identical. So here is identical by descent means one allele present in the forefather, our great-grandfather, is replicated, keep on replication. Then after certain generations, they come together in one individual, which can happen when inbreeding is there. So these type of alleles, which are the replicates of this one original allele, they are known as identical by descent. So like this, then another definition is it represents the probable increase in homozygosity resulting from the mating of individual more closely related than the average for the population. Means percentage increase in the homozygosity in a population due to inbreeding, in a simple word. So this inbreeding coefficient is denoted by capital F, and its value ranges from 0 to 1 or 0% to 100%. You have to remember this one. 0 is when the individual is non-inbred. Say you are non-inbred, so your inbreeding coefficient is 0. If someone is inbred, then inbreeding coefficient will be more than 0. Some value will be there. Then these methods for estimation of inbreeding coefficient, first is part analysis method developed by Shyam, covariance table. Then third is coefficient of co-ancestry or kinship, Malikot. So here we'll discuss the first one, that is part analysis method. But this coefficient of co-ancestry or kinship, this is for PG level. So part analysis I will show here. So this Shyam, he developed a formula for calculation of inbreeding coefficient. Here in one of the group we have done something in the practical class also. Fx, that is the inbreeding coefficient of the X individual, is equal to summation half to the power n plus n prime plus 1 plus Fc. So here let me tell you, Fx is the inbreeding coefficient of the individual. First n is the number of generations from the common ancestor to the first parent of the individual X. N prime is the number of generations from the common ancestor to the second parent of X. Then Fc here is the inbreeding coefficient of the common ancestor. Sometimes the common ancestor itself may be a inbred one. If the common ancestor is inbred, then we have to calculate its inbreeding coefficient also. So that inbreeding coefficient is taken care by this 1 plus Fc. Now, what is common ancestor? Common ancestor means it is a common forefather. We can simply, all of you are well aware of this common forefather. Common forefather is, he is my relative because we have our common grandparent, our great grandparent, like this. Then what is inbred individual? Inbred individual is the resultant offspring due to inbreeding. After inbreeding, whatever offsprings or progenies are produced, they are known as inbred individual. Now here, don't go in that one. Here is this one. X individual, its parents are A and B. A is the first parent, B is the second parent. A is having again two parents, C and D. B is having C and E as its parent. So A and the B are having common this one common parent, that is C and C. Then another D and the E, they are different. So that means A and the B are the two individuals having one common parent. That means A and the B are half brother and sisters. So this style is known as bracket style. This representation of the pedigree is known as bracket style. Then this bracket style we can convert into arrow style. Here, X first parent A, X second parent B, then A C and the D. Then B again C and the E. See here, for this individual X, parents are A and B. These two parents A and B are having a common ancestor C. So C is the common ancestor of X. That means A and B are related individuals. Since mating is between two related individuals A and B, that is known as inbreeding. Due to this inbreeding, offspring X is produced. So X is an inbred individual. Then how to calculate this inbreeding coefficient? Here, counting of the parts. This particular part, I will solve some of the numerical, then I will send in your WhatsApp group so that you can note it down. Okay, here, common ancestor is C. Parts are from C to B, C to A. Then from C to B is one generation, that is N is 1. From C to A is another generation 1. Then common ancestor C is having no information about its parents, therefore it is non-inbred. That means its inbreeding coefficient is 0, 1 plus 0. Then in the contribution to the Fx, you just substitute the formula half to the power 1 plus 1 plus 1 into 1. So it is coming 1 by 8. Okay, that is 12.5%. That means the inbreeding coefficient of the individual X is 12.5%. That means out of the 100 loci present in the individual X, 12.5 loci are homozygote. 12.5% inbreeding coefficient means out of the 100 loci present in the individual X, 12.5 loci are homozygote for any type of genes. Variance covariance table needs a lot of calculations, but let us see, once you people are here, we will discuss it. Okay, now outcrossing, I will, it is a type of outbreeding. Then inbreeding means mating between the related individuals. Outbreeding means mating between unrelated individuals. So outcrossing is a type of outbreeding. Therefore, outcrossing here also, it is mating between unrelated individuals. Since outcrossing and outbreeding, there is some differences in this terminology. Then outcrossing is defined as a type of outbreeding, that is a mating between unrelated individuals belonging to the same breed. Say, for example, your Jersey cattle is there. If one male of Jersey and one female of Jersey, means both the males and the females belongs to the Jersey breed. If they are bred together, and these two males, this male and the female, they are unrelated, but belonging to the same breed. So this mating of the unrelated individuals belonging to the same breed is known as outcrossing. So this outcrossing is the quickest and the most certain method for improvement of the character. Now you please listen to me. See, for example, you are having in our country, we have Sahiwal, we have Haryana cattle, we have Ongol cattle, we have Tharparkar cattle, all those things, pure breds are there. So we want to maintain its purity, but at the same time, we want to bring genetic improvement in the population. But you don't like to mix your pure population or pure breds with some other breeds. Means you want to maintain as such. So in that situation, what should be done? For genetic improvement, you bring some of the unrelated individuals from some other sources belonging to the same breed in your population for their genetic improvement. That is known as outcrossing. That means outcrossing is the type of breeding system by which the purity of the breed can be maintained while bringing the genetic improvement in the populations. Now, Say, for example, crossing of Sahiwal bull from Lucknow with Sahiwal cow from PDC Meerut means different areas. Bull is from another place, cow is from another place. We assume that these two animals, male and the female, from the different parts of the country, they are unrelated. If their breeding is there, that is known as outcrossing. So outcrossing combines with the selection. You select the best male and the female belonging to the same breed, breed it. If they are not related, there is outcrossing. So this outcrossing combines with selection is the only method which were used by our forefathers to bring the genetic improvement of our modern purebreds present at the present in this our time. Then genetic aspects of outcrossing is if the character is highly heritable. Highly heritable trait means more controlled by additive gene action, AGA. So we want to bring certain superior genes from some other population into my population without affecting the purity of my animal. So in that situation, outcrossing is the only means to introduce superior genes from some other population to my population, or from one population to another population. Outcrossing can be used to introduce superior genes which are present in one of the population but absent in some other population. Then what will be the practical use? Commercial animal breeders, like if you are a dog breeder, you are keeping German Shepherd. You are a dog breeder, you are keeping German Shepherd. You don't like to mix your German Shepherd with some other breeds. You want to maintain the purity of your German Shepherd. So in that situation, you will like to purchase a male German Shepherd which is not related to your female. Then they will produce a superior offspring because that male which you purchase is a superior one and not related to your female one which is already with you. So in that situations, outcrossing is the choice of breeding. Then if you assume that your animals are lacking or are not present, are not having some of the genes which you are interested, but you know it in some of the animals of some other farm or some other owner, they are having that particular characteristics or phenotypic expression. That means the animals of that fellow is having those genes which you are interested. So in that situation, how to introduce in your population? That means you purchase one animal from that population and bred with your animal. Since the animals are not related, there is a type of outcrossing. So that way, purity of the breed can be maintained. Okay, students, you please switch on your your microphone. Hello. Hello, dear students. Hello.
Yes, sir.
Okay, for today I will be finishing because you have your next class. Tomorrow again at 1, I will take your class. Okay, theory.
Yes, sir.
Then one more thing is whatever I have this uploaded in your WhatsApp group, you please take it print, okay, and read it. If anything is there, any queries is there, you can talk telephonically also to me, or you can put up the questions in the WhatsApp group. Okay. Then practical things, I will solve some of the numericals, then I will send to you people and you just copy it down for your practical for this one. Because this time due to this present scenario that your exam may be probably online, practical also as well as theory. So in that way, you should have your reading materials and all. If anything is there, any queries and all, in any of the topic which I have sent, then you can contact me. You can ask, you can raise your questions to me. Okay, I am already there to help you or clarify the things. Then tomorrow again, I will take the theory class and get ready at 1 or just 10 minutes before 1. Okay, all the best. All of you are safe now. Hello.
Yes, sir.
Yes, sir.
Okay. Try be careful. Otherwise, you have to save yourself. No one will save you. Okay. All the best and stay safe. Thank you all for your. Okay, bye.
Thank you, sir.
Anyone?
Yes, sir.
Yes, sir.
Okay. Today we'll discuss grading up horse, then thereafter crossbreeding. Okay, then other topics, if we have time, we will try to complete. So grading up, it is one type of outbreeding. That means mating between two unrelated individuals. Here, this word grading up, you please keep it because it generally comes as a short questions, then as an application in genetic improvement program. So those things we will discuss in later part. So in that time only, I will take the name grading up means now what it is the process by which the level of blood of purebred sires are increased in the nondescript cows and their progenies generation after generation. There is one flow chart I will show you so that the nondescript animals are almost similar genetically with the purebred sire. Now try to clear the concept. What we do is say in your respective states you are having cattle that is known as indigenous cattle or native cattle. If they are not considered as a recognized breed in the country, we call them as nondescript cattle. So those nondescript cattle or buffalo or sheep or goat or chicken, that is poultry, we want to bring genetic improvement in those animals considered as nondescript animal. So what we do is we bred them with the well-established breeds. Say, for example, in case of cattle, we have nondescript cattle in Mizoram. If we want to bring genetic improvement for economic traits like milk yield, then what we do is this local cattle or native cattle of Mizoram is crossed with the males of Jersey. Say we want to convert this local cattle of Mizoram into Jersey cattle, then we use the males or sires of Jersey to cross with the females of nondescript cattle of Mizoram. And their progeny will be produced there. Those progenies again will be bred with the males of the Jersey sire from generation to generation. So repeatedly we'll be doing this one. Then after 5 to 6 generations, the blood level of or the genetic inheritance level of Jersey in the nondescript cattle around 99%. So in that situation, this nondescript cattle which possesses around 98% of Jersey inheritance are considered as great animal or means they are almost similar to Jersey. So then what is the utility here? Grading up can be used to improve our mongrel or scrub or nondescript or low producing native stock repeatedly. Then what we do is after around 5 generations, say 5 generations in terms of this one, science we may say 5 generations only, but practically, as you know, in case of cattle, generation interval is around 4 to 5 years. So 5 generations means around 20 to 25 years to convert this cattle of Mizoram into Jersey or maybe into Holstein Friesian or maybe into Sahiwal. So it takes around 25 or 20 years. So after 5 to 6 generations, then the will be around 96 to 98 per animal. That is after upgrading. Those upgraded animals are known as graded animals, are almost similar genetically to the improved breed, that is Jersey here. So in the first generation have a low in this level. In the generation 0, the grades, they are having 0 inheritance. There is hereditary percentage or inheritance percentage from the purebred 0. Then inheritance from the nondescript, that is 10% before start of this program. So after the 1 generation of upgrading, will be 50-50, genetically 50-50 inheritance level will be inherited from both the parents. Then after 2 generations, it becomes 75%. Then after 3, 87.5%. So keep on increasing like this. So the final formula here in the red color, I have given one formula, 2 to the power n minus 1 divided by 2 to the power n. This formula you have to remember. So we cannot remember this blood level inheritance after different generations as such, but if you remember this formula, then you can easily calculate, because in the exam, in your objective type, it will come say after 5 generations of breeding, the inheritance level from the improved breed or recognized breed is around. So by using say 5 means 2 to the power 5 minus 1 divided by 2 to the power 5. So after simplification, you will get that percentage. Okay, then the success of this grading up. Now the thing is, theoretically we have learned then how it can be a successful one in the village conditions or in the field conditions. Here first is the ideals of the villagers. Ideals of the villagers means owners of these non-descript cattle, they should also be very sincerely take part in this type of program. So for example, you have done this, you have initiated or started this upgrading program. After 1 generation, some villagers, they may like or may not like. So means the sincerity of the villagers is also required to make a successful program. Then adaptability of the purebred sire. Say, as you know, here in Mizoram, it is a hilly area. Availability of feed and fodder is limited. So in this situation, which improver breed, that is which recognized breed we like to use in such program. So in that situation, as we know that Jersey, if we want to use exotic cattle, then although Holstein Friesian is the #1 in the world for milk production, we will like to use Jersey because Jersey is small in size, its adaptability is more, and moreover, the feed conversion efficiency of Jersey is much, much higher, and it is a small in size. So very suitable for these agroclimatic conditions of Northeast region. So in that way, you cannot blindly introduce any type of the recognized breed, even if the breed is very good in its own track. So we should see whether it will adapt in these new climatic conditions. Then next is rotation of the sires every 3rd year to avoid inbreeding. As you know, if a male or breeding male is used in a particular area for many years, then this breeding male will start breeding with its own daughters. To prevent that one, after around 3, there is 1 generation interval, the sire has to be removed or replaced by another sire. Then sometimes what happens in the village conditions, all the males of non-descript cattle, they are also available. Then these farmers, what they will do, knowingly or unknowingly, that breeding may take place with these non-descript breeding bulls. Then to prevent these things, what we should do is castration of all those non-descript bulls in the area. Then if no bull is available, there is no bull of non-descript cattle are available, then definitely the farmers will wait for breeding with your improved breed, that is Jersey. Then what we should do is, we want in case of cattle is milk as well as power. So mostly dual purpose breed should be introduced. Then introduction of the AGB, this one I will not speak. Then limitations of grading up is here. Although this grading up is very useful for upgradation of the non-descript cattle for production of more economic traits, but there are certain limitations. The first limitation is, in the very first generation, the improvement is very fast. As you know, the first generation offspring, they will show hybrid vigor or heterosis due to the mixing of the genes from the 2 parental breeds. But in the later generations, the improvement level will be a bit slow. So in this situation, farmers at the very beginning, they are very happy. Then later on, they may complain, sir, there is no improvement in the next generation. You are claiming that there will be improvement, gradual improvement in each and the At the same time, when we talk of heterosis, these reproductive traits having low heritability are again showing more of the heterosis. Then growth, since they have moderate heritability, here again inbreeding depression as well as heterosis, their percentage level is almost moderate or medium. Then carcass characteristics like dressing percentage and all, they are having very high heritability. There is more control by additive gene actions. They shows very little heterosis as well as very little effect of inbreeding. There is very less amount of inbreeding depression. Then types of heterosis here. First is on the basis of genotypes of the parents. So here individual heterosis. See here, what these heterosis may come as a long questions and as a definitions also. What is individual heterosis? What is maternal heterosis? What is paternal heterosis? So here, briefly I'm writing here, but in the later slide, I will be giving the complete definitions. Individual heterosis means advantage of crossbred offspring. As we know, hybrid offspring are showing superiority over their parents. This is known as individual heterosis because the individual is a hybrid, the individual is a crossbred. Maternal heterosis, maternal means mother, as you know. Here, if the mother is a crossbred one, or if the mother is a hybrid, in that situation, the offspring of the hybrid mother or crossbred mother are showing superiority, and due to this influence of the mother, there is a crossbred mother or a hybrid mother that is known as maternal heterosis. The same way paternal heterosis means when we are using hybrid sire or crossbred sire, and due to the crossbred or hybrid sire, the offspring produced from such breeding, they are showing superiority. That type of superiority in the offspring from using a hybrid sire or crossbred sire is known as paternal heterosis. And so individual heterosis here. Maternal heterosis, as I have already mentioned, here is dam. One is crossbred dam, another is purebred dam. Offspring of the crossbred dams, they are showing better performance compared to offspring of the purebred. As you know, crossbred dams, since they are hybrid, their mothering ability in terms of milk production and all that is more. Due to the more milk production from the crossbred dam, the offspring are showing superiority over the offspring of those purebred. This superiority of the offspring of a crossbred dam over the offspring of a purebred dam is known as maternal heterosis. Same way it is paternal heterosis. Okay, then next classification of heterosis is on the basis of the types of estimation. So first one is average or relative heterosis, heterobeltiosis, useful or standard or economic heterosis. So any terminology may come as a definition in the exam. So please take care. Average relative heterosis, when heterosis is estimated over mid-parental value. Mid-parental value means average of the two parents. For example, if the body weight of your mother is 50 kg, your father is 70 kg, then the average of your father and mother, that is considered as mid-parental value, that is 60 kg. So when we are estimating this heterosis by comparing with the mid-parental value, that is the average of the two parents, that heterosis is known as average or relative heterosis. Then heterobeltiosis. When we compare the weights of your father and mother, your father is superior, that is having 70 kg. So when this heterosis is estimated as by comparing with the better parent, so in our situation with the father for body weight, in that situation, that type of heterosis is known as heterobeltiosis. Please remember, heterobeltiosis means heterosis estimated comparing with the superior parent or better parent. Then standard heterosis. When heterosis is estimated over a standard commercial hybrid. So for example, as you know, in case of chicken, poultry, so many hybrid chicks are available in the market. It is well known chicks. Hybrid produced by different poultry industries or poultry breeders. So here standard commercial hybrid. Then you also have produced a hybrid. By a new hybrid is produced. Then we want to compare whether my new hybrid is comparable or better than or inferior to this commercial hybrid available in the market. So if that type of heterosis is known as useful or economic heterosis or standard heterosis. Then uses of heterosis. So number one is it increases the production performance of the animals. So when we cross between two different breeds, two different species, two unrelated individuals, then the offspring shows superiority. So in that way, there will be increase in the production performance of the crossbred or hybrid animal. So it increases the growth rate, reproductive efficiency in terms of age at puberty, age at first calving, then calving interval, and so on. Then by this breeding between two unrelated breeds or species, then we can utilize the good qualities of 2 or more breeds, resulting into a superior offspring. So in that way, we can then. Another is behavior of character in hereditary transmission can be studied. Here I will tell you one thing. Say, as you know, cattle, our cattle having 60 chromosome is crossed with yak. Yak is also having 60 chromosomes, right? When we cross between these cattle and the yak, that is known as species hybridization, because yak and cattle, they are different species. So when they are crossed, that is an example of species hybridization. So in that situation, our local cattle or Indian cattle, Zebu cattle, they possesses hump. It is well known to you. Then yak, they don't have the hump. So when we cross these two species, then the resultant offspring, they don't have hump. That means humpless condition of yak is dominant over the hump condition of Zebu cattle. So in that way, how the characters are transmitted from one generation to another generation can also be done by crossing these two. Then now coming again to this measurement of heterosis. Heterosis is expressed by some traits but not by others. So it is a statement. It may come as a force. Say heterosis is shown by some traits, or heterosis is shown by all the traits. So like that, the language may differ. So in that way, you have to find out whether this statement is true or false. As I have already mentioned, low heritable traits, more heterosis. Low heritable traits, again, in terms of inbreeding depression, more inbreeding depression. High heritable trait, low heterosis, low inbreeding depression. Moderate heritable traits, mild heterosis, or mild inbreeding depression. So traits more controlled by non-additive gene action shows more heterosis. Non-additive gene action, you take this abbreviated word as NAGA, N-A-G-A. Keep in your mind, if any trait is controlled by NAGA, that is non-additive gene action, those traits will show more heterosis. Those traits will show more inbreeding depression. Now, this measurement of heterosis requires the performance. Now, as we know, we want to compare the performance of the hybrid offspring or crossbred offspring. With whom? With the parental breeds. So we are crossing Jersey with, say, Haryana cattle. Jersey is crossed with Haryana. What is the performance of there? What is the performance of Haryana? That is there. Then we have recorded the performance of their crossbred offspring. So there are things. Then when we are using Jersey as a male and the Haryana cattle as a female, one way is there, Jersey as a male, Haryana cattle as a female. They produce crossbred offspring. Then just take the reciprocal way. That is Haryana as a male, Jersey as a female. That is known as reciprocal cross. The first one is known as direct cross. Then another is reciprocal cross. So for the estimation or calculation of heterosis, what we need is the performance records of both the parental lines as well as the offspring of direct cross and offspring of the reciprocal cross. Those things are required because the offspring from the direct cross and the reciprocal cross, their performance may differ. As you know, say when we cross this large white Yorkshire, it is very well known pig breed, with Zobo, that is a local pig of Mizoram. So when we cross between these, let us use first large white Yorkshire as a male, Zobo as a female. Then the offspring produced will have 50% inheritance from Zobo as well as large white Yorkshire. Okay. Then just take the reciprocal. That is Zobo as a male, large white Yorkshire as a female. Again, the offspring produced from such cross is also again having 50-50 inheritance. But the offspring produced from large white Yorkshire as a female, they have superior birth weight because their mother size is more, that is large white Yorkshire. So although these two types of piglets, that is crossbred piglets, they have the similar level of inheritance from both the parents, that 50-50, but the birth weight of hybrid offspring or crossbred offspring from the large white Yorkshire dam are superior as compared to crossbred offspring produced by a Zobo mother. So that is known as difference in the performance of the direct as well as reciprocal crossbred offspring. So heterosis can be measured as mid-parent heterosis, that I told already, then heterobeltosis, then standard heterosis. So this one, mid-parent heterosis, I will be giving in the practical class. I will solve the answers and I will send to you people. So here is past that formula F1. F1 is what? Average performance of the crossbred offspring or hybrid offspring. MP means mid-parent divided by mid-parent into 100. Then high parent heterosis or heterobeltosis. Here is F1, average of the F1, that is a crossbred offspring. Then high parent, that is in case of our body weight, then father's body weight, like this. Then the heterosis person, I don't suggest that you should remember these things. Only thing is you should have some common idea. Then, what are the causes of heterosis? What are the genetic basis of heterosis? Why this superiority is there in the crossbred offspring? So first, maybe there are three possible genetic causes or causes of heterosis. First condition is, as you know, partial to complete dominance, because genes are interacting. Some genes are showing complete dominance, some are showing this partial dominance or incomplete dominance, and some are showing over dominance, and some are epistasis. Let us see one by one. Dominance hypothesis. Here, as we know, two parental lines, Jersey and the Haryana cattle, they are having genes of different types. So here, because it is online class, I cannot show you here, but here I will tell you. Say, for example, Jersey cattle is having capital A in a locus, whereas your Haryana cattle is having small a. So small a, since they are the recessive homozygote, so that will express in case of Haryana cattle. When this Haryana and this Jersey, when they are close, then the small a, that is recessive allele present in Haryana cattle, will be suppressed by the dominant allele present in the Jersey cattle in the offspring, that is in the crossbred offspring. That means each and every recessive allele present in both the parents, they are covered up by the corresponding dominant allele present in the parental line. So it is considered as covering effect of undesirable or deleterious recessive alleles from one parent by dominant alleles from the other, right? So here I am showing here one example. Model A is capital A, small a. That is dominant homozygote is equivalent to heterozygote. That is known as complete dominance. And they are showing superiority over the recessive homozygote. That is tall and the dwarf in case of pea plant, Mendel's experiment. So in this situation, parent 1 is homozygote for some recessive alleles in some of the loci, and again in the parent 2. That is an arbitrary example. You just make the opposite alleles in both the parents. In the exam, no need to remember as such these things, okay? Then in the F1 generation, that is hybrid generations, so the recessive allele present in parent 1, they are covered by the dominant allele present in the parent 2, like that, in the reciprocal way. So therefore, the F1 is superior as compared to their parents. Then over dominance, as you know, what is over dominance? Here is the heterozygote condition is superior to either of the parent. Say for example, father's height is 6 feet, mother's height is 5 feet, their offspring height is 6.5 feet. So in that situation, the offspring is far superior to the superior parent. So that is known as over dominance hypothesis. So such situation is also there in case of animal also. Then This over-dominance theory was first proposed by Searle in the year 1908, and he also has given this term heterosis. Then epistasis. As you know, what is epistasis? It is known as what? Interaction between the genes. That means genes located in the different loci, they are interacting. And what is dominance? Dominance means genes located in the same loci. That is, one is dominant allele, another is recessive allele. They are located in the same locus. They are interacting. Dominant allele is suppressing the recessive allele. That interaction between the two alleles, that is known as intra-allelic or allelic. So capital T is interacting with small t. They are the alleles of the same gene. So this is known as allelic interaction or intra-allelic interaction. That is known as dominance. When capital T is interacting with capital A is present in some other locus. So in that time, that type of interaction is known as epistasis. So due to epistasis, there is interaction between the different genes present in the different loci. There is this increase in the performance of the hybrid offspring, that is known as heterosis. Then how to predict this heterosis? Say for calculation or estimation or measurement, we have to produce hybrid offspring or crossbred offspring. Their performance we have to record, but how to predict before crossing? So this is known as for prediction of the heterosis, what we should know is specific combining ability, SCA. Specific combining ability. There is one combining ability that is known as general combining ability, GCA. General combining ability, GCA, is due to additive gene action. As I told already, heterosis is due to non-additive gene action. That is NAGA. Okay, SCA, specific combining ability, is due to NAGA. General combining ability, GCA, is due to AGA, that is additive gene action. So combining ability, how we can, as last time I mentioned, di-allele crosses. So by inbreeding, I told last time that we can develop so many inbred lines. These inbred lines can be crossed with one another in all possible combinations. Say 3 inbred lines are there, A, B, and C. A can be crossed with B, A can be crossed with C, B can be crossed with C. So in all possible combinations, that type of crossing is known as di-allele cross. So from this di-allele cross, we can estimate general combining ability, that is additive gene action, specific combining ability, that is due to non-additive gene action like dominance interactions. So here is one formula. Generally, it comes in your junior research fellowship examinations. Once you have completed your BBAC degree, if you are interested for higher studies, then in that situation, this formula is generally asked. So in the F1 hybrid, that percent heterosis is equal to summation dy square. Okay, please keep in your mind dy square, where D is the directional dominance. This one, directional dominance. It is not complete dominance. It is not partial dominance. It is not no dominance, or it is not over dominance. We use a word that is directional dominance. Okay. Then what is Y? Y is the difference in the gene frequencies between the two parental populations. So let us take, as you have already learned in population genetics, there is Hardy-Weinberg law. There are gene genotype frequencies. Many things you have calculated and you have learned. So let us take this Haryana cattle and Jersey cattle. For a particular gene, if their frequencies are same in Jersey and in Haryana, so these two breeds or populations, they are having equal gene frequencies. So then in that situation, what will be the value of Y? Y will be 0 because there is no difference in the gene frequency. Then this type of Haryana, this type of Jersey, when they are close together, we know because the factor Y is 0. So in that means, see for example, if we cross, as you red Sindhi is a male breed. Then let us take another one. Haryana is a 12 purpose. I am giving one example because these questions comes as an applied question. Now please listen carefully. Let us have 3 breeds: Sahiwal, male breed; Red Sindhi, male breed; Haryana, dual purpose breed. So let us cross. First is Sahiwal with Red Sindhi. They produce hybrid offspring or crossbred offspring. Sahiwal cross with Haryana. They also produce crossbred offspring. These crossbred offspring produce from these two different types of crosses, that is Sahiwal with Red Sindhi. Both are mixed breed. That means the gene frequencies responsible for milk production, they are almost similar in case of Sahiwal and the Red Sindhi. Therefore, there will be very little heterosis in their offspring, that is crossbred offspring. Whereas this Haryana, since it is a dual purpose breed, the genes responsible for milk production that is there, but that type of gene is different from those present in Sahiwal cattle. That means Sahiwal cattle and the Haryana, they have differences in their gene frequencies. So the crossbred offspring produced from their cross will have more heterosis. So that way, in exam, they may ask these type of things. The offspring produced from crossing between Haryana and the Thar Parker will produce more or high heterosis as compared to offspring produced from Sahiwal and the Red Sindhi cross. That is true. So you have to see that type of breeds. Okay. Then in the F2 generations, then it is F2 hybrid, the percentage of heterosis observed in F1 is reduced to half. That means if 10% heterosis is there for any character in F1 hybrids, then what will be the heterosis percent in case of F2 generation? That is 5%. That is half of 10%. If it is 10% in F2 generations, then what will be the amount in F1? That will be double. That is 20%. Okay, be careful for your exam. Then, why this reduction in heterosis from F1 to F2? Now, just now we discussed that the amount or percentage of heterosis from F1 to F2 is reduced to half. Why there is reduction? This is commonly asked in justifications. So as you know, when capital T is a Mendelian genetics, let us go back to Mendelian genetics. Capital T, one is dominant homozygote, one parent. Another is small t, recessive homozygote. When they are crossed, they produce capital T and small t. That means in F1 generation, each and every individuals are having capital T and small t. Means they are all heterozygotes, right? When this F1 is bred with F1, that is known as selfing or inter-seed mating. So as we know, in the F2 generation, there will be capital T, there will be capital T, small t, there will be small t, small t. Means in the F2 generations, the homozygote may be in the form of dominant homozygote, that is capital T, or small t. They are observed in the F2 generation. As we know, heterosis is due to heterozygosity. So in F1, each and every individual, they are heterozygote. Whereas in F2, some are heterozygote, some are homozygote. So due to this homozygote condition, the performance level is reduced. So on an average, the average production performance in the F2 generation is reduced due to the presence or observed presence of homozygote individual. So as a result, there is reduction in the heterosis percentage in the F2 as compared to F1. Okay. So this way, then from F2 generation onwards, say F3, F4, then there will be very little changes in the percentage of heterosis. So this is the end of this slide. Okay, then I will go for another slide. Okay, this is very important topic, crossbreeding. Right, this I will try to complete. As I already told, crossbreeding means breeding between or mating between two unrelated individuals belonging to the two different breeds. Say Thar Parker bull, when it is with Haryana cow, there is an example of crossbreeding. Then Parker bull, as we just now we discussed that upgrading. So after the end of the upgrading, those high grade means those nondescript cattle, almost similar to Jersey cattle, they are known as very high grade. If this type of cross is also known as crossbreeding. And it is also sometimes called as crease crossing of two breeds or rotational crossing of 3 or more breeds. This we will discuss in the later part of the slide. Then, what are the objectives of crossbreeding? See, please keep in your mind, I will be giving these slides, these hands out to you people. Crossbreeding is the third tool of the animal breeders, okay, which can be utilized for genetic improvement of our livestock animals. Then other two tools are selection and inbreeding. Please keep in your mind, 3 tools: selection, inbreeding, then crossbreeding. Crossbreeding is the third tool, right? Then, as we have discussed about the heterosis or hybrid vigor, the chief reason for crossbreeding is to bring an increase in the heterosis, right? Then, these are the advantages of crossbreeding or merits of crossbreeding. The objective of crossbreeding was to cross between 2 different breeds so as to increase the production performance of the crossbred animals by exploitation of the heterosis. Then let us discuss now point-wise what are the merits of crossbreeding. First is introduction of new genes from one breed to another breed. So let us take Holstein Friesian we are using for crossbreeding program in our country, right? Why we are using Holstein Friesian? Why not our own native cattle like Sahiwal, Ghir, Red Sindhi and all? What we feel as an animal breeder, we thought that our native cattle like Sahiwal, Red Sindhi, Ghir and all, they are having genes responsible for milk production, but we want superior genes for higher milk